Okay, so let's talk about polytropic processes. And this is a reciprocating pump, and it's got air in it that we're going to assume is ideal. And it's initially at 67 C and 0.95 bar, and it's got 0.103 meters cubed of air. And it's going to undergo a change in volume to 0.02 meters cubed. And it's going to happen polytropically, meaning it's going to be a polytropic process. And polytropic process follows PV raised to a power is equal to a constant. So just in general, as we discussed before, any polytropic process will follow this equation. This is not, again, I'm going to reiterate, not an equation of state. It's not. It describes what happens when I go from state 1 to state 2. It describes during this change how the pressure and volume are related. It does not describe, for example, if I want to look here, if I wanted to know, if I want to know if I had the pressure and I try to find the volume for that process, for that state in the isolate. Like if this didn't exist, this would not hold for this state. It only describes what happens when it undergoes this change. So it is not an equation of state. And as a matter of fact, we're going to assume that air is an ideal gas. So for our case here, we have two states. We're going to have state 1 and state 2. Here, we're going to assume PV equals nRT. Here, we're going to assume PV equals nRT. And between this and this, we're going to assume it's PV raised to 1.3 is equal to some sort of constant. That's what we're going to do. So, so again, let's review that. We were given basically most things for state 1. We're given some things for state 2. We're being asked to find the mass of the air that's involved because that's not given to us. And we're asked for the final temperature, which we do not have. We also don't have the final pressure, and we're going to get that as well. The change in internal energy, the work, the heat. Okay, and this is an ideal gas, so we don't have to use tables if we don't want to, and we can easily get away with PV equals nRT. They're also nice giving us the CV, the specific heat, not the heat capacity, because it's in a per kilogram basis. They could have not, and if they didn't, the back of the book has a bunch of CVs for air at different temperatures, and you can interpolate or use a relation, etc. So we're going to assume it's a constant CV for this case. All right, so what we're going to do now, I'm going to look at state 1, and I'm going to write what's given to me, and I'm going to look at state 2 and see what's given to me. And I'm going to fill in the blanks, and it's just as per usual. We're trying to define the states, get all the pressure, volume, temperature, moles or mass for each of the states, and then afterwards we will use other relations to find things like U, work, Q, usually the first law of thermodynamics to do that. This is a closed system, so we're going to just assume it's the first law of closed systems. And we are given that this is T is equal to 67 degrees Celsius. And then we are given that the total volume and at state 1 is 0.103 meters cubed. And we know that the pressure is 0.95 bar. And we don't have the mass. That's the other thing we could possibly get, mass or moles. We don't have that, and we're being asked for the mass in that case. This 67, by the way, we don't want Celsius because it's not an absolute scale, so we're going to just convert to Kelvin. For state 2, so let me just subscript everything 1, 1, 1. M is the same because it's a closed system. I'm going to have T2, which I don't have. I'm being asked for that. Final temperature. I know the final volume. That was nice of them. They gave me that. That's 0.02 meters cubed. I do not have the final pressure. And again, the mass is the same. Okay. Obviously, we don't have the U's. We don't have any of the U's. We don't have any idea for the work. We don't have any idea for the Q. Okay, so the first thing that I would do, well, there's several ways of going about this. Okay, so I'm looking at for temperature here. And I know that this is an ideal gas. And so I can relate temperature, pressure, and moles and volume using the ideal gas. I don't have a lot of those variables, so I can't apply directly for state 2. I also know that I can do, I can relate 2 states of an ideal gas by dividing it by itself. And since the moles don't change, I can also say that this is the case. Again, well, that's great, and we probably will use this. We don't have enough information. We have everything for state number 1, but for state number 2, we only have V2. So we don't have P2 to get T2. So we need to get P2 to get to T2. So that's one thing. That's one way of going about this. The other way of trying to get the pressure and the temperature here is by just applying the ideal gas law for state 2. Again, we don't have the pressure, we don't have the temperature, we also don't have the moles or the mass. So there are 2 ways of going about this. I can find the mass, and from the mass find the moles, and from the moles apply this. Or I can just find the mass because I'm being asked for the mass and not use it for this, and then just use this to get and not use that, and then I'll have to find another way to get the pressure. So let's try to first get the mass. So I'm going to apply the ideal gas law for state number 1. So I know for state number 1, I have P1 V1 is equal to nR T1. And I am given stuff in bars, meters cubed, and Kelvin. So I got to select an R that's got all of those units in it. And that's fine. So you go look at the list of R's that you have. And the one that will fit the bill here is 8.314 times 10 to the minus 5th. And that's going to have bar, meters cubed, moles, and K. Okay, so let me just kind of dot that around so we're not going to confuse that. Okay, so I'm going to apply that directly here. I have everything, so I'm just going to find N. So N is going to be P1 V1 over RT1. Okay, and from the moles, I can easily get the mass. So P1 is 0.95 bars. The volume is 0.103. The R is this thing. So I'm just going to write R because I'm lazy, but it's this. I'm going to put 8.314 times 10 to the minus 5th, and it's got bars, meters cubed, and then divide by mole K. And that's cool because I'm multiplying by the temperature, which is 340 K. So that will give me moles, right? So the bars cancel, the meters cubed cancel the Kelvin, and I get 1 over mole, which gives me moles. And so when I get this, I find that N from this calculation is 3.46 moles of air. Again, I don't want moles. That's not what I'm being asked for, and it's going to be unhelpful for a lot of things because we're given things like, for example, the CV here in terms of kilograms. So we want to convert this to kilograms or to grams. So I'm gonna put grams, and then later we can play with it with kilograms. So we know that the molecular weight for air, and if you don't remember this, this is in the back of the book. It's like 28.9. When we call it 29 grams of air per mole. And so that means that the mass is going to be the moles times the molecular weight. And you can see moles would cancel moles, and I get grams. So it's 29 times 3.416. Times 3.46 moles. And finally, I get that my mass is going to be 100.3 grams of air. Okay, So what I'm going to do, so this is part A of what I'm being asked. I'm going to I'm going to put that as an answer to up here. So I know that the mass here, we're going to erase all the stuff that we don't need it anymore, is 100.3. So I could put that here directly. It's 100.3 grams. That's something we solve for. Okay, so now I have 100.3 grams of air, and that's going to stay constant throughout the entire process. So that's good. Like I said, now we can assume that this is the same here. We also know that we know the moles here, which was calculated. It was 3.46 moles. So for example, in this equation, to try to find state 2, I don't have P2, I don't have T2, but now I have V2 and as well as N. Still not enough. If I'm trying to use this thing here, same problem. I don't have P2, I don't have T2, I have everything else. So I gotta have another way to find either P or T, and I do. So as I mentioned before, we have state 1 going to state 2, and within state 1, the PV equals 100 T holds. Within state 2, PV equals 100 T holds. During this process, we have PV to the 1.3 holding. So I'm going to actually use this idea to try to get my final pressure. So what that means for this process, what this means to me, that the initial pressure times the initial volume raised to the 1.3, that's equal to a constant. And it's also true that P2 raised to the same times V2 raised to the same exponent is going to equal to the same constant. So in essence, since these two are the same, I can say that this is the case. Again, I will again urge you to remember this is not an equation of state. This is only because it's undergoing a process. This describes the process that's undergone between state 1 and state 2. It does not describe the gas. It describes the process. So I am trying to find P2 because I have the second volume, I have the initial volume, and I have the initial pressure. And the units don't really matter as long as they're consistent. You don't even have you don't have to have the same system of units. You don't have to be SI or anything like that. If this pressure is in PSI and this pressure is in PSI, that's fine because they cancel out. They don't have any bearing on the volume. So you can mix any sort of two units as long as the two pressures are the same units and the two volumes are the same units. So that's the only caveat here. So in our case, we don't have P2. We have P1 and it is in 0.95 bars. And we have that the two volumes are the same unit, so that's good. So these meters cubed will cancel. The fact that P1 is in bars will mean that P2 will be given to me in bars when I calculate it. So I'm going to put it all in. I have 0.95 bars times the initial volume raised to the 1.3, and that's going to be equal to what I don't know, P2 times the final volume, which I do know, and it's 1.3. So now it's just punching into the calculator, you know, this times this divided by 0.02 to the 1.3. And when you do, you're going to get that in bars, and you get that the final pressure is 8 bars. Okay, so we weren't asked for this explicitly, but we kind of need it. So we calculated that P2 here is 8 bars. So I'm going to put that here as a calculated result. Okay, so the red is what we didn't have recalculated. Cool. So now we got that. Now that I have P2, well, then now I can find T2, which we were asked for. So again, two ways of doing that. You can use the combined gas law, or you can use the ideal gas law just applied for state 2, whatever you want. So what I'm going to do is actually use this. I think it's easier. I don't have to deal with moles or anything. Not that dealing with moles is very difficult. We have the moles. but it's going to give me the same value anyway. But I have these numbers in front of me, so I'll just use that. So P1 here is 0.95 bars. V1 is 0.103. And it's being divided by P2, which is, we just calculated as 8 bars. And V2, which is given to me as 0.02 meters cubed. All that is equal to the ratio of temperature. And again, they must be in Kelvin or Rankine. And then T2. Again, just like with the polytropic equation of state, not equation of state, no, polytropic equation, the units don't really matter as long as they're consistent. So I could have had this volume in gallons for all I care, as long as this is gallons and this is gallons. It has no bearing on the other units because they cancel. So they have to match. So volumes have to have the same volume unit, the pressures have the same unit, and the temperature will have the same unit. So when I apply all of this, I find that the temperature is 506 Kelvin. And so now I have defined the temperature, the states are completely defined as far as I'm concerned. Between the two states, I have the pressure, the volume, the temperature, and the mole/mass for both states. And so now here, if I'm looking at the question here, we did the mass of air, we got that, we got the final temperature. Now we're being asked for all this stuff. And this is first law stuff. So we can use the first law to find it for the most part. Okay. All right, so I'm going to erase all of this. We have all these values. For an ideal gas, so we're going to put that here because we need that. We don't need these PVs anymore. So we have that. What we know for an ideal gas, that the change in internal energy of an ideal gas is going to be, well, let's do specific. Is going to be mCV integrated dt from T1 to T2. Okay, and then that's true. That's specific volume, specific heat at constant volume. This is mass. If the specific heat was in terms of moles, I would use N here. Because in terms of mass, I'm using the mass. And so there are two ways of doing this. One way is to just assume a constant value, which this question does. The other way, which will probably be a little more common for a course, and you can look at other examples where I did this, is we're going to assume that CV is a function of temperature and then integrate it. And the back of the book gives you the functions of temperature for different substances. But in this particular case, we're just going to assume a constant value. Since we are going to assume that CV is constant with temperature, we can pull it out of the integral. The mass we are also assuming is constant with temperature because it's a closed system, so we can pull it out of the integral. So what we get for this specific case, not for every single case, but for this specific question, the M and the CV come out of the integral, and we're going to get this. And so in reality, for this specific question, it's mCV delta T from T1 to T2. And that should give us the specific internal energy, okay, in terms of kilograms or grams. So we know that delta U then is equal to, well, the mass, and we calculated the mass to be 100.3 grams. We know the CV is 0.7204 joules per grams Kelvin. Okay, I'll give a word about that in a second. And we know that the final temperature is 556 minus 340 is the initial temperature. And so the kelvins will cancel the kelvins, the grams will cancel the grams, and I'm going to get delta U in joules. And I was wrong. This is total U because I'm multiplying it by the mass. This is not specific internal energy, it's just total internal energy, which is what we want. So delta U in our case, once you substitute all of that in, is 15,607 joules. Okay. So that gives us that. So that here I'm going to write delta U is 15,607 joules. Okay. So I want to talk two words about that. If I I'm not going to change the calculation. I'm not going to throw any other numbers right now. If I omitted the M here, then this is the specific internal energy. Okay? Meaning that that means that I divided through by M. And that's fine, that's valid. And you could do that. So that would give you this if you had that. But we're asked specifically for the total U. If you want just the specific U, that's fine too. You just divide through the mass. Let's say, for example, we didn't have the mass. We can divide through by the mass and get it on a per mass basis. That's one thing. The other thing that you may have noticed I just did, and may have been a bit distressing, is that the CV here in the question was given as 0.7204 kilojoules per kilograms Kelvin. And I just threw that in there and said it was joules per gram. And so what I wanted to notice is that kilojoule per kilogram, kilo just means 1,000, right? So kilojoules means 1,000 joules, kilograms means 1,000 grams. So basically the 1,000s cancel. So whenever I see kilojoule per kilogram, it's the same as joules per gram. That's what I was able to do that. If you're not comfortable with that, that's fine. Then you would just put this here as 0.1003 kilograms, and you would put 0.7204 kilojoules per kilogram Kelvin, and you'd put this delta T, well, it's the same delta T as this, and what you would get is 15.607 kilojoules, which is the same as that. But now you have it in terms of kilojoules, and if you want to convert it to joules, you just multiply by 1,000 and you get this. So it's okay if you're not comfortable with that little bit. Well, I just did that. I can just get rid of the kilograms, and call it joules and grams. That's fine. You can stick with whatever the units are. You'll always get it right if you just stick with the units. It's one of those tricks that I happen to use a lot. I just cancel the kilo with the kilo if they're there. I cannot do that, for example, if I have joules per kilogram Kelvin, then I can't do that because there's no kilo to cancel this kilo. So just an aside, but that's something that you will encounter often. The back of the book has a bunch of kilojoule per kilogram stuff, and you can easily call that joules per gram. Okay, now. Okay, so to get the work for this process is a polytropic process. So in general, as we know, work is equal to the integral of PdV, and we can derive it, and I derived it in the notes, but for a polytropic process, specifically for polytropic process, we were able to derive that P2V2 minus P1V1 divided by 1 minus N should give me the work. So what this N is, again, this is the exponent of the polytropic process equation. And in our specific question, we could see that N is 1.3, we were given. It isn't always, in our case it is. So what we could do is we could use the final pressure and volume, the initial pressure and volume, and the N is equal to 1.3 to get the work. And so we see that work is going to be equal to P2 is 8 bars. Volume 2, sorry, is 0.02 meters cubed. Minus P1 V1 is 0.95 bars. V1 is 0.103. And all of this divided by 1 minus 1.3. Again, this 1.3 is specific to this question because that's the exponent that we had. Punch all of this into the calculator and you get 0.2, what is it, 0.717, but this is in units of bars times meters cubed, which is not joules, not SI in any way. So we need to get rid of bars to get into pascals, because once we get pascals, Pascal times meters cubed, that will give us joules. So we have to just remember that 1 bar is 100,000 pascals. 1 bar is 100,000 pascals. And then that's a simple thing. You just multiply this by 100,000 and you get 20,717 joules. And I think I removed the negative. There's a negative here. There's a negative and this is a negative. Okay, so that means that the work is negative. Work is negative 20,717 joules. Okay, so that's that. And then lastly, to get to Q, which is what we want, we have delta U, we have work, now we have Q. That is just the first law for closed systems, assuming that delta K and delta P, delta KE and delta PE are 0. We have the change in internal energy, that's 15,607. We don't have Q, obviously, minus negative, negative 20,717 joules. And when we do that, we get that heat is negative 5,110 joules. And that means that heat was released in this process.